So how can the short-term scheduler, the CPU scheduler, make the decision of which process will be allowed in the CPU and which process will be forced out or removed from the CPU? Based on what? On a scheduling algorithm. Who will choose the algorithm? It's you, the operating system designer. What are the criteria that you have to take into consideration while choosing your scheduling algorithm? We have actually 5 main things to consider. We want to maximize the CPU utilization. Keep the CPU busy as long as possible. We want to maximize the throughput, number of processes that finished execution within time unit. We want to minimize the turnaround time of a process. That is the total of the time that the process took from the moment it started to the moment it terminated. That includes the time it runs in the CPU, that it was waiting for input-output operation, that was waiting in the queue. And we want to minimize the waiting time of a process waiting for the CPU. Last but not least, we want to have the smallest possible response time. And this is very important for the user convenience. After I click, I need to see an immediate response. This is what appeals the user. And user satisfaction, if you remember, was one of our main objectives. With this in mind, we will look into a few scheduling algorithms. We want to maximize CPU utilization, maximize throughput, minimize turnaround time, minimize waiting time, and minimize response time. The simplest, most straightforward way to deal with processes needs to be executing on the CPU is first come, first served. All we are going to look at is the arrival time. When did the process enter the ready queue? Here we have 3 processes, P1, P2, and P3. P1 needs 24 time units to finish execution. P2 needs 3 units to finish execution, and P3 needs also 3 units to finish execution. P1 arrived first, it will go first. Its waiting time is 0 because as soon it was the first in the CPU made. P2 will start after P1 finishes. Then P3 will start after P2 finishes. Clearly, first come, first serve is a non-preemptive algorithm. If we look for waiting time, P1 waiting time was 0, P2 was the time that P1 needed to execute, which was 24. P3 will wait for both processes to execute. That made its waiting time 27. It's an average of 17 time units of waiting time. And for P2 and P3, that looks like a long time to wait to be executing for only 3 time units. So first come, first served is easy, straightforward, easy to implement, straightforward, and but it doesn't take into consideration the actual execution time of a process. That usually leads to increase the waiting time of the processes with shorter execution time. If by any chance B2 and B3 arrive before B1, the scenario will be totally completely different, where waiting time for B1 would be 6 because B2 needed three time units and B3 needed 3 time units. Waiting time for B1, B2 will be 0, for B3 will be 3. And that means average waiting time will be only 3. But we don't have control on which process will be first in the ready queue. Do we? No, we don't. That made operating system designers or generally scheduling algorithm designers think of another way to look at how they select processes to be executing. They said, let us consider the time a process needs to finish execution. And let us allow processes with smaller amount of time needed to go first. That will definitely minimize the waiting time. And this is one of the main objectives of any scheduling algorithm. So, shortest job first. We'll look into what is the length of the CPU burst a process needs, and then select from the processes in the ready queue the one with the shortest needed CPU burst. The problem here is, how can we actually know how long the CPU time a process needs? For this, we shall see how we will predict it later. Okay, let us look into an example first. Here we have 4 processes, P1, P2, P3, P4. In the example provided, their arrival time and their first time, the time they need in the CPU. The arrival time, the time they arrive into the ready queue. So P1 arrived in the ready queue in time 0 and it needs 6 time units. There was no one in the ready queue before P1, so P1 will be immediately allowed into the CPU. P2 came at time 2 and it needs 8 time units. P3 came at time 4 and it needs 7 time units. Where P4 arrived at time 5 and it needs 3 time units. all three processes has arrived in the CPU while P1 was still executing in the CPU. After P1 finished execution, you will see that the three other processes were in the CPU waiting to be selected. So now I'm afraid this chart is not correct because the chart did not take into consideration the arrival time. If we took into consideration the arrival time, P1 will go first. Then we will select the shortest time from the other three, which are P2, P3, and P4. So it will be B1 go first, B4 next, B3, then P2. But if we discarded the arrival time, if they didn't give us arrival time in the example, then we will have 4 processes with 4 burst times, and this will be the only major we take into consideration. Like in real life, arrival time is crucial because it is completely meaningless for P1 to be in the ready queue with no other process and not to be allowed in the CPU either way. So this chart is discarding the arrival time. If we ignore the arrival time, we assume that all processes arrived at the ready queue at the same time, then P4 will go first, P1 will go next, P3 will go third, and B2 will go last. Average waiting time for P4 will be 0, for P1 will be 3, for P3 will be 9, and for P4 will be 16. It's an average of 7 time units. So how can I determine the length of the CPU burst? Briefly, I have two options. I can either estimate it based on similar or previous behavior, or I can predict it from past lengths of CPU bursts. Shortest job first, as we have seen it here, is a non-preemptive algorithm, just like first come, first served. There is a version of shortest job first that is a preemptive shortest job first called shortest remaining term first.